welcome back, everyone. Sorry about these problems. We had a computer crash, and we had to restart the whole process, and then we were waiting a little bit for everyone to show up. But we're now all set up and ready for Nikhil's talk. Before we start, let me just announce what's coming up. So a couple weeks from now, the talk will be given by Lorenzo Orecchia on algorithms for max flow, I think. 2 weeks after that, November 20th, we're not sure yet, and then December 4th, we'll have David Stirrer talk about, I think, lower bounds for extended formulations. So today we're very pleased to have Nikhil Srivastava from MSR India talk. So Nikhil got his PhD in 2010, was it, with at Yale with Dan Spielman. Then he was a postdoc at IAS and Princeton, and now he joined MSR India in 2012. So Nikhil has done a number of breakthrough works in graph sparsification, the construction of good expanders, and the Cadison-Singer conjecture that he's going to tell us about. So it's funny because I, before the talk, I pulled up Nikhil's PhD thesis, and there's a chapter there. It's a one-page chapter that's called the Cadison-Singer conjecture, and in that chapter, he observes that the conjecture can be seen as a generalization of the two main results that he has in his thesis. And if only these two results could be unified and combined together, then the conjecture would follow. So I guess it took maybe a couple of years, but this happened, and Nikhil is going to tell us that story. So please.
Oh, thanks a lot, Thomas, and thank you for inviting me. This is the first online talk that I've ever given. So okay, so this is joint work with Adam Marcus and Dan Spielman. So it's about the solution of this Cadison-Singer problem. So let me start by telling you what that is. So this is a problem that came out of mathematical physics. It came out of trying to get axioms for quantum mechanics. And it started with the work of Dirac in the 1930s, who came up with this bracket formalism for describing quantum states. So in this formalism, states are vectors in some kind of Hilbert space, and observables are self-adjoint matrices, and there's a notion of measurement and so on. And Dirac developed this, in his book Principles of Quantum Mechanics. And one of the things he described how to do in this book is how to find a representation for a compatible family of observables. Okay, so what that means mathematically is how to find a single orthonormal basis that diagonalizes a family of commuting self-adjoint operators. So commuting operators in quantum mechanics correspond to observables that can be measured simultaneously, that do not have an uncertainty principle. So this procedure in his book was sort of one of the important constructions. And at the heart of it, the way he did it is he sort of relied on this sort of basic fact from linear algebra, which is that if you have two matrices A and B which commute, then A and B have a set of common eigenvectors. Okay. So unfortunately, in actual physics, bras and kets cannot be taken to be vectors in a Hilbert space. So first of all, you can have observables that can take infinitely many values. For example, energy. So you at least need a infinite Hilbert space. That's okay. But then you can have observables that take continuous values like position and momentum. And the self-adjoint operators corresponding to this are actually in uncountable Hilbert space. But more importantly, you can't take the states to be vectors. You need something like a delta function. Okay. So essentially, what Dirac did in his book about diagonalizing matrices and so on doesn't actually apply to quantum states because they're not vectors. So this led Murray and von Neumann to develop this theory of C-star algebras, which you can view as a generalization of linear algebra designed to contain these more general objects that you need for quantum mechanics. Okay? And what Cadison and Singer asked in 1959 is, within this more general framework of C-star algebras, does Dirac's procedure for finding a representation work? So is it possible to diagonalize commuting operators in this C-star algebra setting? Okay. And what this boiled down to mathematically was the following question, which became called the Cadison-Singer problem. And it says, I mean, it's a question about bounded operators on separable Hilbert space. So it says that does every pure state on the algebra of diagonal operators on L2 have a unique extension to a pure state on the algebra of bounded operators on L2? Okay. So, you don't have to understand what this means. The point is that this became sort of an important question in operator theory, and many approaches were developed to solve it. And one of the approaches was sort of initiated by Anderson in 1979. And Anderson reduced this to a question about finite matrices, to a very simple, basically combinatorial question about finite n by n matrices that we all know and love. And this was called the paving conjecture. Okay, so then in 1991, Ackermann and Anderson further reduced this to a question about finite projection matrices. So they showed that this, Cadison-Singer problem is actually equivalent to some simple statement about projection matrices. After that, there were many other reformulations, and it was sort of observed that this conjecture is equivalent to a number of conjectures in, different areas of mathematics. And one of the reformulations was due to Weaver in 2002, who came up with sort of a discrepancy theoretic formulation of this question. Okay, so this is what I'm going to describe in the talk, and the main result of this talk is a proof of Weaver's conjecture, which then implies by all these equivalences, all these other conjectures as well as the Cadison-Singer conjecture. Okay, so let me tell you what Weaver's conjecture is. So it's a conjecture about partitioning sets of vectors in Rn in a balanced way. Okay, so what does that mean? So given m vectors in Rn, v1 through vm, I'm going to be interested in looking at their second moments in various directions. Okay, so if I have a test direction u in Rn, a unit vector, then the second moment in direction u is the sum of the projection of u onto the vi squared, right? Which can be written as a quadratic form in this matrix, sum of vi transpose. Okay, so I'm interested in the quadratic form of the vectors vi, which corresponds to the second moment. So here's an example. You have four vectors in R2, and I can look at the second moment along the x-axis, so I can compute the projections onto the first coordinate squared, and I get some number. I can compute the second moment in the y-axis, so this is another test vector that's orthogonal to the first one, or I can compute it in any old direction. I can pick any unit vector. Okay, and the most useful way to think about this is that this quadratic form defines an ellipsoid associated with these vectors. Okay, and basically if you look at the value of the quadratic form in all the directions, you get an ellipsoid. And the principal axes of this ellipsoid are the eigenvectors of this matrix, sum over I vi transpose, of which this is the quadratic form. And the lengths of these axes are the eigenvalues. Okay. So what I'm going to be interested in is, given a set of vectors, partitioning it into sets which preserve this ellipsoid, this quadratic form. Okay. So let me consider the case so I'm going to be interested in the special case where the vectors are isotropic. And what that means is that this ellipsoid is a sphere, so the quadratic form is just equal to 1 in every direction. The second moment is equal to 1 in every direction. And in matrix notation, what this means is that the sum of vi transpose is equal to the identity. Okay? So this goes by many different names. You can call this a John's decomposition, or a frame, a tight frame, and so on. But basically, it's a decomposition of the identity. And what I'm going to be interested in is, given such an isotropic set of vectors vi, I would like to partition it into two subsets, such that each subset such that each subset is nearly half spherical. Okay, so that means I want to color the vectors red and blue in such a way that when I look at the two parts, the ellipsoid that I get, the quadratic form, is nearly equal to half. Okay, so here's a bad partition. Okay, so if I partition it this way, I get two ellipsoids that are skewed. Here's another bad partition. What I'm interested in is something that looks like this. Okay, so I'm interested in red-blue coloring so that when I look at each part, it's close to a sphere. And formally, what that means is I would like the eigenvalues of the red part to be close to a half. So I'm going to say contained in this interval 1/4 to 3/4. Okay. So in particular, bounded away from 0 and 1. So notice that any subset of these vectors will have eigenvalues between 0 and 1. That's sort of trivial. What I want is a partition into red and blue so that each part has eigenvalues that are bounded away from 0 and 1. Okay. Okay. So let me observe that this is equivalent to just requiring an upper bound on the eigenvalues of each part. Okay. So if I can find a partition so that each half has eigenvalues upper bounded by 3/4, then that suffices. And the reason is that because the original set was isotropic, the red part is just equal to identity minus the blue part. Okay. And so the eigenvalues of the red part are just 1 minus the eigenvalues of the blue part, and getting an upper bound on both also automatically gives me a lower bound on both of them. Okay. So this is what I would like to do, and I would like to do this always. So the problem is, given any set of vectors, split it evenly in this manner. Okay. Unfortunately, this doesn't hold all the time. Okay. And here's an example where you can't do it. So if you have 4 vectors and 2 of them are orthogonal and really big, and the other 2 are also orthogonal to each other, but they're much shorter, and maybe they're like they're like a Hadamard basis or something. Then what happens if I try to partition this into 2 balanced sets is the following. So if I put both the big vectors in one set, then I get one very big sphere and one very small sphere. Okay, so these are not close to a half. On the other hand, if I take one big one and one small one in each side, I get very skewed eigenvalues. Okay, so you can sort of see it geometrically in this picture. Because there are some vectors that pretty much account for the entire quadratic form, there's no way of splitting the set into pieces. Basically, because the vectors are too chunky. Some of the vectors. Okay, so if you have really big vectors, you can't do this. And Weaver's conjecture, the conjecture which I said was equivalent to the Katz-Singer conjecture, is that if all the vectors are short, then a good partition always exists.
Nikhil?
Yeah. Yeah.
Why do you need the short vectors? Sorry, stupid question.
Okay. So the canonical example of a set that you cannot partition is just an orthonormal basis. Okay. So if I have just n vectors in Rn which are orthonormal, so just EI, then they're a decomposition of the identity, right? Now, if I want to partition this into 2 sets, one of the sets, I mean, both one of the sets has to be degenerate. So I only have n vectors, and I mean, basically, there's no way to split an orthonormal basis into 2 linearly independent sets. And what I'm asking for is something stronger than linear independence. Does that answer your question?
Yeah, I think so.
Okay. Yeah. So. Okay. I mean, another way to, another thing to look at is the one-dimensional case. In the one-dimensional case, this just becomes bin packing. If you have a bunch of numbers that add up to 1, and you want to split them into subsets that are close to a half, if the numbers are big, you cannot do it, right?
Yeah. No, I just meant, to demonstrate why big vectors are an obstacle, you don't need the short vectors, right? You just take.
Yeah. You just take an orthonormal basis. Yeah, sure. But okay. So Weaver's conjecture is that if all the vectors are short, then this balanced partition always exists. And this is the theorem that we prove. So we prove that given m vectors in Rn, which are a decomposition of the identity, and the norms are bounded by epsilon. So think of epsilon as a constant, like 1/10 or something. Then there is a partition of the vectors into 2 subsets, T1 and T2, with the property that if you look at each subset, if you look at the sum of the outer products of the vectors in that subset, then the norm is bounded by half plus 3 epsilon. Okay. So in particular, this implies that the quadratic forms have eigenvalues between half plus 3 epsilon and half minus 3 epsilon. So notice that this sort of, gives you a non-trivial bound when epsilon is less than 1/6, right? So a bound of 1 would be trivial, and as soon as epsilon is strictly less than 1/6, I get a bound that beats 1. Okay. And this dependence on epsilon can be, shown to be optimal. Okay. So before I tell you, so are there any questions about the statement of the theorem? Okay. Okay. So before I, tell you about the proof, let me give you some finite applications of this theorem in finite dimensions. So this is a theorem about finite dimensional linear algebra, and let me just give you some, I showed you this infinite dimensional application to Caddis-Singer, but let me show you some finite applications.
And Nikhil, just one thing more, and the theorem also proves the other direction, right? That all the eigenvalues are at least half minus 3 epsilon.
Yes, yeah. So by what I showed you on this slide, right?
Right.
The eigenvalues of each part are 1 minus the eigenvalues of the other part. So in particular, yes, it proves that all the eigenvalues of each part are between half minus 3 epsilon and half plus 3 epsilon.
Yeah. Okay.
Yes. Okay. Okay. So let me show you some applications. So here's an application to graph theory, and this is sort of how we originally got into this problem. So suppose you have an undirected graph G. You can define its Laplacian matrix L of G, which is this sum of outer products over the edges. So for every edge ij, you look at this matrix delta I minus delta j transpose, which is just an n by n matrix with 4 non-zero entries that look like in this picture. Now, what's the thing I'm interested in is the Laplacian quadratic form. So this matrix has a quadratic form x transpose Lx, and it's easy to see that this is equal to the sum of differences squared over the edges of the graph G. Okay, so it's sum of xi minus xj squared, and you take the sum over the edge. So this is sort of a natural notion of energy on a graph, and it actually corresponds to a physical notion if you look at electrical. If you look at the graph in an electrical network or a spring network. Okay. So I gave you a theorem. I told you about a theorem about partitioning quadratic forms, and I gave you a way to represent a graph as a quadratic form, right? So this should give me a way to partition graphs into pieces which approximate it. So given a graph G, I can look at the Laplacian matrix, right? So for every edge, I have this incidence vector, which is just a +1 in I and a -1 in j. I look at these vectors. There's some vectors in Rn. They might not be isotropic, but I can apply a linear transformation to make them isotropic. Okay, so basically, I take a graph and I turn it into a set of vectors. Now, assuming the vectors are short, which I'll get to in a moment, the theorem that we proved tells you that you can partition the vectors into 2 subsets, each of which approximate half of the original set. Okay, so they're very close to half of the original quadratic form. Now the thing is, these vectors correspond to edges, so every subset of vectors corresponds to a subgraph, right? So in particular, turning turning these vectors back into graphs, I obtain a partition of my original graph G into 2 graphs H1 and H2, okay, a red graph and a blue graph. And the guarantee of the theorem is that the Laplacian quadratic form of H1 is going to be very close to the Laplacian quadratic form of G multiplied by a half, okay? So basically, the theorem tells me that I can split a graph into 2 edge disjoint subgraphs, such that the Laplacian quadratic form of each one approximates that of the original, approximates half of that of the original. Okay? So each part approximates the whole. Now, if I apply this theorem recursively, so this gave me a way to split a graph into 2 pieces which approximate it in this Laplacian sense, I can keep doing this recursively until I get sparse graphs. And it yields the following theorem. It says that if you give me any transitive graph G, you can partition it into sparse graphs. So that means graphs with constant degree, such that each graph is a constant factor approximation of the original graph. Okay? So by constant factor approximation, I mean the Laplacian quadratic forms are within a constant, which also means that all the cuts are preserved up to a constant. So for example, if I apply this to the complete graph, it tells me that I can split the complete graph into n constant degree expander graphs, which will actually be sort of close to being Ramanujan graphs. And this generalizes this theorem of Fries and Malloy, who showed that you can partition expanders into sparser expanders. And the real point of this theorem is that it actually applies to much more general graphs. So you don't need the complete graph. If you can give me the hypercube, and this will give a partition of the hypercube into log n edge disjoint subgraphs, each of which has the same cut structure as the hypercube. Okay? And coming back to this condition on the norms of the vectors that you get from a graph, their lengths, their squared lengths, are actually just equal to the effective resistances of edges in the graph. So if you have any graph with bounded effective resistances, you can partition it into edge disjoint subgraphs, each of which approximate. Okay? So that's an application to graph theory. Here's another application. This is to I guess signal processing. You can think of it. So it's about the discrete Fourier transform. So if you have a vector x in Cn, its Fourier transform x hat is just this usual change of basis onto this basis of exponentials. And then there's a sort of very elementary and useful fact about this, which is sometimes called the uncertainty principle, which says that x and x hat cannot both be simultaneously localized. So a signal cannot be sparse in the time domain and the frequency domain. And the way this is written is that the support of x times the support of x hat, the product is at least n. Okay. So in particular, what this means is that if you have a vector s, if you have vector x that's supported on some squared n coordinates, then its Fourier transform is supported on at least squared n coordinates. Okay, so applying this theorem about splitting quadratic forms to restrictions of the Fourier transform yields the following stronger theorem. It tells us that for every subset of the vertices size squared n, there's a partition of the frequencies of the Fourier domain into squared n buckets. Okay, so that if I look at any vector that's supported on this set S, its L2 norm is spread evenly among these buckets. So you can view this as a quantitative version of the usual uncertainty principle. So this doesn't just tell you that the Fourier transform has support at least squared n. It tells you how the mass is distributed. And again, this is sort of just a straight up application of the theorem. You can write this restricted Fourier transform as a quadratic form, and then you can partition it. But the basic take-home message of all of this is that the reason the theorem is useful is that it says that anything you can encode as a quadratic form, you can split into pieces while preserving the spectral properties. Okay. And the reason it's useful is that you can encode many different kinds of objects as quadratic forms, like graphs.
Hey, Nikhil?
Yes.
Hey, is this algorithmic, by the way?
No, not algorithmic.
Okay.
Yeah.
Do you know it even in some of these specific applications? Like, do you know what the bucketing should be for the Fourier transform?
Nope.
Oh, okay.
No. So that's a good question. None of this is algorithmic. So, okay.
Nikhil?
Yes.
So, for example, can you use that to do things like RIP for Fourier matrices?
Use this?
Yeah.
That's a good question. So it seems like you should be able to use it. I mean, I wouldn't say do RIP, but
I mean, like show that it exists, show that there exist a few rows of the Fourier matrix.
So I don't know. I mean, that's a good question. I mean, the uncertainty principle has been used in RIP type constructions with certain parameters, right? So you could try to use this instead. I mean, So the known applications of this so far are mostly in analytic number theory and signal processing, but yeah, sure. Okay. So so these are some applications of the theorem, and let me now say something about the proof. So here's the main theorem, right? So given m vectors in Rn that have norm with most epsilon and add up to the identity, there's a partition of them into two sets so that each part has eigenvalues bounded by half plus 3 epsilon. So I'm going to use this positive semi-definiteness notation to say that one matrix is less than the other in the PSD ordering. Okay. So this just means the eigenvalues are most half plus 3 epsilon. Okay. So I want to find a partition, right? So I'm given m vectors, and I want to find a partition that's balanced in the sense that The quadratic form is split evenly in every direction. So how am I going to find this partition? So one natural thing to try is try a random partition. So what I'm going to do is put each vector in T1 with probability half, and in T2 with probability half. So my partition has two parts. Okay. And what I would like then is that each part has eigenvalues bounded by this half plus 3 epsilon, has small eigenvalues. Okay. So I'm going to write. I want the eigenvalues of two matrices to be bounded. So I can actually write this as the eigenvalues of a single matrix by doing this little trick. So I'm given vectors in Rn, but instead I can look at this 2n by 2n matrix, whose upper left block is just the first half of the partition, and lower right block is the second half of the partition. Okay. And then it's easy to see that the norm of this matrix is just the maximum of the norms of the two parts. So what I really want is I want the norm of this this block matrix to be bounded by half plus 3 epsilon. Okay. I want a random partition. I want to pick the vectors randomly, and I want this to happen with some probability. Okay. So let me observe that this is a sum of independent rank 1 matrices. Okay. So for every vector vi, I'm independently choosing whether to put it in the top half or the bottom half, right? And when I add all these things up, I get the matrix I'm interested in. This is a sum of independent rank 1 random matrices. And I want its norm to be small with good probability. So they're very well-developed tools for analyzing sums of independent rank 1 matrices, just like there are tools for analyzing sums of independent bounded scalar random variables. So okay, so I'm going to use red to denote random variable. So red vectors are random and black ones are deterministic. Okay, so here's one form of this so-called matrix Chernoff bound due to Rudolphson. What it says is that if you have m independent random vectors v1 through vm, okay, they don't have to be identically distributed; they just have to be independent. With two properties. One is that the expected sum of their outer product is equal to the identity. Okay, so the expected matrix that you get is the identity. Another way to view this is the sum of the covariance matrices is equal to the identity. And also the vectors are bounded, so they have norm bounded by epsilon, where epsilon is some constant. Then what Rudolphson showed, and this can be traced back to work of Luce Picard and Pisier, is that the expected norm of sum of vi transpose is at most 1 plus epsilon square root log n. Okay? So 1 is the norm of the expectation, right? I told you that the expected matrix is the identity, so 1 is the norm of the expectation. This is saying that the expected norm, which is a larger quantity, is at most 1 plus this epsilon square root log n. Okay? Now, if you just use this to analyze a random partition in this in the problem that we're interested in, you get a partition for which each side has norm bounded by half plus epsilon square root log n. Okay. So what that means is if your vectors have length less than 1 over square root log n, then you get a non-trivial bound. So this is useful in some settings, but it's not enough for the applications which I mentioned earlier. And let me mention that this log n factor is unavoidable if you do a random partition. Okay. So the example that shows that it's tight is very simple. If you take the vectors to be basically a bunch of copies of the canonical orthonormal basis, so just vectors with a 1 in one coordinate, then if you take a sum of a bunch of independent copies of this, it corresponds to throwing balls into bins. So it corresponds to throwing like 100 n balls into n bins. Okay. And then the norm of the matrix is just a maximum number of balls in a bin, which we know is going to be like log n. So you need a log factor here if you're going to do things randomly. So in that sense, this is tight. Okay. So the theorem, the main theorem that we prove is actually gets rid of this log factor in the Chernoff bound. So what we prove is that if you have m independent random vectors in Rn satisfying these properties, then the probability that the norm is at most 1 plus 3 epsilon is non-zero. Okay. So this removes this log n factor, but it's weaker in that we only get a non-zero probability. So this Chernoff bound, you actually get a bound on the expectation, and you can actually show that the probability of being much larger than this decays exponentially. Here, we can control the deviation at a much smaller scale. There's no log factor. Okay, so you want to think of this as a balls and bins allocation where every bin has like 3 balls or something. But we just show that it exists. We can't show it exists with high probability because it doesn't. It's a rare object. Okay. And then just using this instead of the matrix Chernoff bound to analyze the random partitioning procedure gives the theorem. It gives you a partition so that each half is bounded by this half plus 2 epsilon. Okay.
So Nikhil, can you hear me?
Yes.
So how do you use this to prove your result about the sums? So what are the random variables?
Yeah, so the random variables, so this is sort of the reduction. So you start off with vectors vi and rn, right? And the random variables are actually random vectors in R of dimension 2n. Okay? Mm-hmm. And for each vi, you define a random vector, which either puts it in the top half or the bottom half. Mm-hmm. And then the sum of the outer product of those vectors, those are these red vectors, is going to be this block matrix. So that's the reduction. You basically just put it in the top half or the bottom half. Is that clear? Is that okay?
Yeah, that's also where the half comes from, and now we scale everything up by 2. Yeah.
Yeah, you rescale everything by 2, and that's where the 1 turns into a half. Exactly. Okay. So yeah, you want to think of this as a improvement of the Chernoff bound without the log factor, but at also not with high probability. Okay. So I'm going to tell you about how to prove this theorem in the case when the vectors have support 2. Okay. So what I mean by that is that each random vector v1 through vm has a 2-point distribution. It takes value vi naught with probability half and vi1 with probability half. Okay, and this is certainly enough to do the Cadison-Singer thing that I talked about earlier. In our case, each vector is just going to place vi in the top block with probability half and in the bottom block with probability half. Okay. So in this setting, the vectors are independent. The probability space has a very simple structure. The probability space is just the hypercube in m dimensions. It's just bit strings of length m, right? Because for every I just have to choose either one point or the other one. So points in the probability space I'm going to denote by omega, which are bit strings of length m. And I'm going to be interested in the characteristic polynomial. So in the end, I'm interested in eigenvalues of matrices, right? Eigenvalues of matrices are roots of characteristic polynomials. So I'm going to be interested in the characteristic polynomial corresponding to every point in this probability space. Okay. So for any point omega in this probability space, I get a particular setting of these random vectors vi. Okay. I'm going to denote this by vi of omega. Okay. So it's a particular setting, which in the reduction corresponds to a particular partition. And I'm going to let chi of omega denote the characteristic polynomial of this particular setting of the vectors. So it's a determinant of xi minus some vi transpose, where the vi's are now set according to this bit string omega. So there are 2 to the m points in the probability space. There are 2 to the m polynomials. Each polynomial has real roots because it's a characteristic polynomial of a symmetric matrix. Okay. Okay. So with this notation, the theorem I want to prove is the following. So if you have independent random vectors v1 through vm, then there exists an omega in the probability space so that the norm at that point is at most 1 plus 3 epsilon, right? So as I said, the norm is just the largest eigenvalue of the characteristic polynomial. So that's just sort of what the characteristic polynomial is. And then I define this notation for the characteristic polynomial. So the characteristic polynomial of omega, I'm going to call chi of omega. So I want to prove that given such independent vectors, there exists one setting of them. There exists one point in the probability space. So the largest root of that characteristic polynomial is bounded by 1 plus 3 epsilon.
Now, Nikhil, do you know anything about the probability?
No. So as I said, in general, the probability can be certainly exponentially small. For example, in the diagonal case, in the balls and bins case, this corresponds to an allocation of balls into bins with constant maximum load, right?
But for example, if you replace the 3 with 300, could you hope the probability to be exponentially small but in exponent going to 0?
No, I mean for the same type of reason. I think. I mean, if you replace it with log n, then you can get.
No, log n will be high probability, but I mean,
Yeah,
if you replace it with a large constant, it's still going to be exponentially small in this example,
yes.
but the exponent will go to 0.
Sure. As you make the constant bigger and bigger, the exponent would get better. That's true.
Okay.
I don't know the exact dependence, but yes.
Okay, so that's true in general, I say.
Yeah. So I mean, I think that's a good direction. I don't know. I don't have any estimates on what these probabilities are, and that would be a good thing to know. Okay. So this is the theorem. Okay. So you know, really, what I'm given these random vectors, I really want to show existence of one polynomial with roots bounded by 1 plus 3 epsilon. Right? So the main idea is to consider the expected characteristic polynomial. Okay. So I'm just going to, I have 2 to the m polynomials. I'm just going to average all of them and get a polynomial. So this is the expected characteristic polynomial of sum of vi transpose, where these vi's are these random vectors. Okay. So usually adding polynomials is sort of a useless thing to do. Like expected characteristic polynomial of a random matrix doesn't usually have that much to do with. I mean, it usually doesn't have much to do with the matrices. But it turns out in this case, we'll be able to relate the behavior of the expected characteristic polynomial to particular polynomials in the family. Okay, so in particular, I'm gonna you know, these polynomials have these special interlacing properties, which I'll tell you about in a moment, which imply that there must exist an omega, so that the largest root of the characteristic polynomial at omega is at most the largest root of the expected characteristic polynomial. Okay, so that's sort of the main proof technique. So this gives you sort of a clear 2-step plan for proving this theorem. The first step is to prove what I just mentioned on the previous slide. Show that there must exist some omega, some one polynomial whose largest root is at most the largest root of the expected polynomial. And then I actually wanted to show this is at most 1 plus 3 epsilon. So now I'm going to have to bound the largest root of the expected polynomial. So the second step is to do that. Okay? So let me do the first step first. And let me just reiterate that this is very different from the usual type of averaging argument. So this is not saying that there exists you know, an omega, so the largest root at omega is at most the expected largest root. So that's sort of a trivial statement. Here I've taken the expectation inside the largest root, right? So I'm comparing one polynomial with this purple polynomial to the sum of exponentially many polynomials. Okay. So the basic question I need to understand here is, you know, how do the roots of the average of polynomials behave, right? So the simplest case, you know, I can think of is I have 2 polynomials, P0 and P1, and the basic question is, what do the roots of the individual polynomials Pi have to do with the roots of the expectation? Okay, where the expectation is taken with respect to some distribution. So so in general, there doesn't have to be much of a relationship, right? So here's a canonical bad example. So P0 and P1 are quadratic polynomials, x minus 1 squared and x plus 1 squared. They have real roots. The roots are just minus 1 and plus 1, right? However, when I add them, I get a polynomial that's strictly positive everywhere because it's a sum of squares. So it doesn't even have real roots, right? So I wanted to compare the roots of the individual polynomials to the roots of the expectation, but here the expectation doesn't even have real roots. So I don't have a chance of doing that. Again, you know, there are many bad examples. Here's another one, but there are also some good examples. So here's a good example. If my 2 quadratics have the property that the roots alternate, as shown in this picture, then I can actually show that their average, this purple polynomial, its roots are contained in the convex hulls of the corresponding roots of the original polynomials, which is exactly the sort of relationship that I want. Okay? So basically what we do is we identify sort of a general sufficient condition for this averaging argument to work, and this condition is based on interlacing. So let me define what interlacing is. So So a polynomial Q of degree n minus 1 with real roots alpha 1 through alpha n minus 1. We say that it interlaces P, where P is a degree n polynomial, if between every two roots of P, there is a root of Q. So the picture is as shown here. Between every two betas, there's an alpha. So that's the definition of Q interlacing P. And given a bunch of polynomials, I'm going to say that they have a common interlacing if there exists one polynomial which interlaces all of them. Okay, so this is a sort of very central concept, and this turns out to be a sufficient condition for relating the roots of individual polynomials to the roots of the average polynomial. So the main theorem about common interlacing is this: if P0 and P1 have a common interlacing, then the largest root of one of them is at most the largest root of the expectation. Okay, and I'm assuming P0, P1 have are of the same degree and they're monic. So the leading coefficient is 1. So if they have common interlacing, then one of them does as well as the expectation. So this has a very simple proof, which I'll just show you on this slide. So here are my two polynomials of degree 3, P0 and P1. Okay, they have three real roots. Now they have a common interlacing. Okay, so that's a polynomial of degree 2, which interlaces both of them. So let me look at the roots of that polynomial. Let me call them alpha 1 and alpha 2. So between every two roots of P0, there's an alpha I, right? So what these alpha i's do is that they split the real line into is that they split the real line into 3 intervals, okay? So that each interval contains exactly one root of P0 and one root of P1. Okay, I'm assuming there's no multiplicity here, but it also works out when there is. Okay. So I split the real line into 3 closed intervals, and each interval contains exactly one root of P0 and one root of P1. Okay. So I'm interested in the largest root, so let me look at the last interval. Okay. So I can shrink this interval so that it's right up against the roots of P0 and P1. Okay. So I can assume that this interval is just from the largest root of the red polynomial to the largest root of the blue polynomial. Okay. And the property that I have here is that each of these polynomials changes sign exactly once. Now, at the end of the interval, both polynomials are strictly positive, okay, because they have positive leading coefficient. So when you go to infinity, they're strictly positive. And each one changes sign exactly once. So at the beginning of the interval, they're both non-positive, right? So in particular, any average of these polynomials is strictly positive at the end of the interval and non-positive at the beginning. So, and it's a continuous function, so it must have a root inside the interval, any average of the polynomials. And then therefore, the largest root of the, the least largest root, which is the root of the red polynomial in this case, is at most the largest root of the expectation. And that's the proof of the theorem. So are there any questions about this?
Nikhil?
Yeah.
So can you say that the root, like the roots interlace, if the roots of the interlacing polynomial are sorry, the roots of the expected polynomial interlace these intervals?
No. So they don't. So interlacing is a notion that's, I guess, defined for polynomials. So you can't really say that all you can say is that the roots of So
you showed one root. You said that one root is there's
yeah.
at least one root. Can you show there's exactly one root?
Yes, you can show there's exactly one root. And actually, here's what exactly you can show. You can show that the kth root of the expected polynomial is contained in the convex hull of the kth roots of the individual polynomial.
Okay, that's what I wanted.
Yeah, that's probably
interlacing
what you wanted,
was not the right term.
Yeah,
right.
So that's what you wanted. So you're right. There's nothing special about the top interval here. As long as you know that they're monic, you can basically you can find intervals where the sign changes once and the same argument works. Okay. So yeah, basically the statement you get is that the kth root of the expected polynomial is in the convex hull of the kth roots of the individual polynomial. Okay. So this is what we need for our averaging argument to work, right? Common interlacing. And it turns out that there's a very sort of systematic way to prove that a common interlacing exists. So, this notion of common interlacing is very old, and there's a sort of folklore result, which is also contained in the book of Fisk, which shows that the existence of common interlacings is equivalent to certain real rootedness statements. Okay, so here's the lemma. Suppose you have k polynomials that are monic and real rooted. They have a common interlacing if and only if all convex combinations of them have real roots. Okay, so for all alpha I adding up to 1 that are non-negative, some alpha I pi has real roots.
By real roots, you mean all the roots are real?
Yes. Yeah. So have real roots means all the roots are real. Yes. So yes. So okay, and this is sort of a 2 or 3 line exercise that you can do, and it's instructive. Okay. So this gives me sort of a clear approach to proving that my averaging argument works. I want to prove that the polynomials I'm interested in have a common interlacing. So I want to prove all convex combinations have real roots. Unfortunately, they do not have a common interlacing. Okay. So it's pretty easy to see that the polynomials in this example do not have a common interlacing. However, there is a lot of interlacing structure hidden in there, okay, in the following sense. So what are my polynomials? Okay, so for every omega, for every setting of these vectors, I'm interested in the characteristic polynomial of the sum of vi transpose set according to omega, right? So it's a sum of rank 1 matrices. It's a characteristic polynomial of sum of rank 1 matrices. Now, if I look at the partial sums, then I can find a lot of interlacing structure. Okay, so concretely, if I look at the characteristic polynomial of v1 transpose, just one vector, right? And then I look at a partial sum of length 2. I add 2 vectors. Then Cauchy's interlacing theorem tells me that the sum of length 1, the characteristic polynomial interlaces the sum of length 2. Okay, so that's equivalent to the fact that if you have a matrix, then the eigenvalues of any minor interlace the eigenvalues of the matrix. Okay? So there is some interlacing structure in my polynomials. I mean, they don't have a common interlacing, but somehow if I look at these partial sums and try to extend them, then I see interlacing happening. Okay, so what you do is you identify a weaker sufficient condition, okay, which also guarantees this property that you want, this averaging property, and exploits this interlacing structure that's inside these sums of rank 1 matrices. So here's the weaker condition. So it's a definition. Suppose you give me a collection of real rooted polynomials f of omega indexed by the hypercube. So 2 of them polynomials, all with real roots, monic. Okay. I'm going to say that this is an interlacing family if the expected polynomial has real roots for all product distributions on the hypercube. Okay. So previously I told you that common interlacing is equivalent to all distributions having real roots. Here I only want product distributions. Okay. And now with this definition, the easy corollary is that if you have a set of polynomials, which is an interlacing family, so if all product distributions have real roots, then the same conclusion holds. There exists one polynomial, so that its largest root is at most the largest root of the expectation. Okay. And the proof is very simple. It's just inductive application of the theorem I showed you on the previous slide. You just set, I mean, you're interested in bit strings of length m. You just set the bits 1 by 1. It's sort of a conditional expectation type of thing. Okay. Okay. So this is the condition that I'm going to use to show what I want to show. Okay. So I wanted to show that there exists one polynomial such that its largest root is the largest root of the expectation. By what I just told you, it suffices to show that these polynomials, these characteristic polynomials of sums of rank 1 matrices, are an interlacing family, which just means that for all product distributions on the vectors. So what does that mean, right? So originally, my distribution of vi was uniform on 2 different vectors, right? Now I'm going to look at bias distributions. So the bias, it doesn't have to be half. It doesn't have to take probability. It doesn't have to take 0 with probability half and 1 with probability half. It can be any bias. So I would like to show that for all such product distributions, the expected characteristic polynomial has real roots, and that will guarantee what I want. Okay. Okay.
Nikhil?
Yes.
So, but for this application, it seems that you don't really have to use all the bias distributions. It's enough to have, right, that some value is maybe can take all values and the others are either fixed to 0, 1 or
absolutely, absolutely. That's exactly right. You only need a special case, but this is a sufficient condition.
Okay.
And well, this is going to be a special case of an even more general thing, which is then going to be easy to prove. So
okay.
you're right. Okay. So here's an even more general thing. So here's the main real rootedness theorem that's sort of at the center of this. It says that given any independent random vectors, v1 through vm, okay, not necessarily identically distributed, their expected characteristic polynomial has real roots, has all real roots. Okay. So in particular, any product distribution on my, on my vectors that I had is a special case of this, right? It's some expected characteristic polynomial of some random vectors. So this is what we call a mixed characteristic polynomial. Okay. And well, all of these things have real roots, so all of these product things have real roots, and what I want follows. Okay, so how do I prove this? So I want to, I have this sum of 2 to the n polynomials. Each of them has real roots, but as we saw, adding polynomials does not preserve real roots, right? So how do I show that this has real roots? So there's sort of a philosophy about how to do this kind of thing at this point, which has been developed for many decades, mainly starting in the statistical physics, which is that if you want to show that a univariate polynomial has real roots, you should not try to do it directly. So basically, if you want, often when you want to study a univariate polynomial, it's beneficial to view it as a specialization or some kind of transformation of a multivariate polynomial, and then prove that the multivariate polynomial has real roots, which I'll define what that means. And then use that to deduce that the univariate specialization also has real roots. So basically the reason for this is that in multivariate polynomials, you somehow have a lot more space to move around, which will become clear in a moment what I mean by that. But yeah, the philosophy is you want to prove univariate results, first prove multivariate results, and then specialize. So this was, Alan Sokal said this in one of his surveys, and then Borchea and Brandon have taken this to have proven some incredible results in the last 5 or 6 years. Which I'll also talk about later. Okay. Okay. So I'm gonna apply this strategy. So I want to prove that this polynomial has real roots, right? So I'm gonna try to view it as some image of a multivariate polynomial. Now, what is a real rooted multivariate polynomial, right? So this is sort of a central concept that we need. It's called a real stable polynomial. So this was defined probably in the 50s. And here's the definition. So an n-variate polynomial p with real coefficients is called real stable if given any z, so that all the coordinates zi are in the upper half plane, strictly in the upper half plane, p of z is not equal to 0. So it has no roots with all entries in the upper half plane. That's a definition of real stability. Okay. An equivalent definition, which might be easier to think about, is that a multivariate polynomial p is real stable if all of its univariate restrictions, so you look at all lines, which are pointing strictly into the positive orthant, all of those have real roots. Okay, so that's a definition of real stability. Now, here are some very preliminary things to notice about real stability. So a univariate real stable polynomial is real rooted. Okay, because if you have a univariate polynomial, its roots occur in complex roots occur in conjugate pairs. So if it has some non-real roots, then one of them is in the upper half plane. So a univariate real stable polynomial is real rooted. So as I hinted at earlier, the reason we're interested in real stable polynomials is that they have amazing closure properties. Okay, so this is a very strong condition, but it's closed under a lot of operations. Okay, so here are 2 operations under which it's closed. So one is setting variables to be equal to real numbers. So if you have p, which is real stable, then if I set one of the variables to be any real number alpha, it's also real stable. Okay. Now this is not obvious. So what would be obvious is if I set alpha to be a number in the upper half plane, right? That just follows from the definition. However, I can set alpha to be a number on the real line. And the reason this is true is that limits of real stable polynomials are real stable. Okay. So I mean that fact follows from generic complex analysis, but this is also the sort of central fact that makes the multivariate setting much more powerful and expressive than the univariate setting. That limits of real stable polynomials are real stable. So for example, in this closure property, I could set alpha to be a real number, not just a number in the upper half plane. So this is actually the essential thing that is not present in the univariate theory. This is what gives you all the extra room in the multivariate theory. The other fact that I'm going to use about real stable polynomials is they're closed under certain differential operators. So if I take, if I have p, and I look at p minus the partial derivative of p with respect to some zi, so I'm going to denote this by I minus partial zi times p, this is also real rooted. This was proved by Lieb and Soka in 1981, and it's a short exercise. It's basically just the Gauss-Lucas theorem. Okay. So these are the closure properties that I'm going to use, and you know, I mean, I need to start with something that's real stable, right? So I showed you what preserves real stability, but I need to start with something. So there's a sort of canonical polynomial that one always starts with in these proofs, and it's the following. So it's a determinant. So Bourget and Brandon wrote this in their paper in 2008, that if you have positive semi-definite matrices A1 through AK, then the polynomial determinant of some zi ai, where the zi are variables, so this is a k-variate polynomial, is real stable. Okay. So this also has a 2 or 3 line proof that you can do as an exercise. The point is that this theory, I mean, so far most of the application, the way this theory is used is it's almost like a calculus. Okay. If you want to prove something is real stable, you always start with this polynomial, and then you apply various closure properties, such as the 2 that I described earlier, to arrive at the polynomial you're interested in. Okay, and at this point, the list of the closure properties have been more or less completely characterized by Bourget and Brandon. So this is a very sort of safe, like systematic area to work in. Okay, so here's the plan, right? I know this is real stable. I'm gonna apply closure properties to show that my expected characteristic polynomial is real stable. Okay.
Nikhil?
Yes.
So since you said that all the closure properties are more or less characterized, is there a formal sense in which all real stable polynomials can be obtained by starting with this polynomial and applying the closure properties, or
no? So that is not known. So what is characterized? Okay, what's really characterized is all linear transformations preserving real stability. That's characterized. Okay. Yeah. So there's no theorem that says you can always start with a determinant and end up at what you're interested in. So it's not a proof system, if that's what you're asking. Is that okay?
Yeah.
Okay.
Thanks.
So okay. Okay. So the success of this depends on one identity here, which I'm going to call sort of the central identity, and it says the following. So suppose I have m independent random vectors v1 through vm. So these should be red, I guess. And their covariance matrices are ai, let's say. Okay. Then the expected characteristic polynomial of sum of vi va transpose, the thing I'm interested in, can be written as follows. So it's some kind of multivariate characteristic polynomial. It's a determinant of xi plus some zi ai, where ai are the covariance matrices. Okay. Some differential operators are applied to that, one for every variable. So you have I minus partial with respect to zi, one for every I. And then at the end, all the auxiliary variables are set to 0. Okay, so the thing in the determinant is an m plus 1 variate polynomial. The differential operators give you another m plus 1 variate polynomial. You set all the z's to 0, you get a univariate polynomial. Okay. Now, this is sort of a very useful identity because on the left you have this sort of large sum of polynomials, and on the right you have a very succinct representation of this in terms of nice operations like these differentiation operations. And it reveals several interesting things about the characteristic polynomial. So one of them is that this just proves to you immediately that the expected characteristic polynomial only depends on the covariance matrices. It doesn't depend on the actual distributions, right? It only depends on the AI. Okay. So the proof of this is also sort of it's like a half a page. You can do it by Cauchy-Binet, or James Lee has like a 3-line proof using rank 1 updates. But in all these proofs, the basic principle is that random rank 1 updates of these expected characteristic polynomials on the left-hand side correspond to these differential operators on the right-hand side. Okay. So in the univariate setting, you have a random rank 1 update. In the multivariate domain on the other side, you have a partial differentiation operator with respect to a variable. Okay, so you can try to prove this. It's a good exercise. But once we have this, so just the mere existence of this representation pretty much proves the theorem, right? So here's the proof. So this determinant is real stable, right? Because it's a sum, because all the matrices AI are positive semi-definite because they're covariance matrices. So that's this Borchet and Brandon result, right? These operators preserve real stability because real stability is closed under, well, these differential operators, okay? Setting variables to 0 also preserves real stability. So this polynomial is real stable, which means this polynomial is real stable, but this polynomial is univariate, so it must be real root. Okay, so that's the whole proof. Just basically, once you have the identity, the proof is just, it's there. Okay. So are there any questions about that proof? Okay, but I mean, the basic idea is that you know, you can only see the structure when you write this thing as a multivariate polynomial. It's not, I mean, it's not possible. At least I don't know how to write this as a sequence of nice operations on univariate polynomials. You really need these extra variables. Okay. So that finishes the first part of the theorem. So you know, I just showed you that all expected characteristic polynomials have real roots because of the existence of this identity, which means in particular all product distributions of these chi of omegas have real roots, which means it's an interlacing family, which means there must be one polynomial which does as well as the expected polynomial. Okay, so that's the end of the first part. Okay, so maybe this is a good time to take a break. So there's going to be a second part which is much shorter, but maybe we can take a break. Are there any questions?
Yeah, Nikhil?
Yeah.
I just want to ask you two questions.
Mm-hmm.
So at some point you said that the dependence on epsilon was optimal. Did you mean that the factor 3 was optimal, or that it being linear and epsilon was optimal?
I meant that it being linear and epsilon is optimal.
Okay.
So, I mean, okay, the 3 is actually like 1 plus epsilon squared.
Okay.
I mean, the first order term is optimal too, actually. The second order term is what may not be optimal.
Oh, the 2 epsilon is optimal.
Yeah, that's optimal.
And the other question I have is, so
well, okay, I mean, if you really want to know, it's 1 plus square root 2 times epsilon the whole square divided by 2. But the leading term is optimal. Yeah.
And I just had one other question, which is, so you mentioned that you proved that you can partition into 2 pieces, and then if you want to partition into more pieces, you can do this recursively.
Yeah.
And I guess if you do it recursively, your error builds up.
Yep.
Right? So do you know whether you can potentially, say, like split into k pieces in one shot, not recursively, and do better in terms of the error parameter?
So you cannot really do, so the recursive thing gets you up to first order, the optimal error parameter, just because you can use it to construct things that are close to Ramanujan graphs out of the complete graph. So yeah, so you may be able to improve the constant term by doing something else. So at this point, it seems to me like the recursive partitioning is as good as, I mean, there's a way to do a one-shot reduction too, by just like I did the block reduction into 2 blocks, I could use k blocks, right? But if you want 2-sided approximation, that seems to be not doing better. So.
Nikhil?
Yeah?
Yeah, I was just not totally clear on the part of the reduction for the statement you just proved that goes through the product distributions. So what was it about setting 1 bit at a time? I just I think I missed that.
So I skipped the proof of that. Okay, I didn't say. So it actually requires a proof, but basically here's what you do, right? So I have I have a random polynomial, expectation of f, right? I would like to show that there exists some setting of the bits which does as well as the expected polynomial. So what I'm going to do is look at the expectation of f conditioned on the first bit. Okay. So there are 2 conditionings of the first bit, 0 and 1, right? So that gives me 2 polynomials. Let me call them F0 and F1. Okay. This product distribution thing tells me that those two polynomials have a common interlacing. Because if you have all product distributions, you can encode all conditionings, basically. And then I get that there exists some, setting of the first bit omega1 so that, so that the expected polynomial conditioned on the first bit does as well as the expected polynomial conditioned on nothing. And then I repeat this with the second bit, and so on. Does that make sense?
Yes.
So it's like this method of pessimistic estimators in computer science, except we're not doing conditional probabilities. Instead of probabilities, we have roots of conditional expected polynomials.
So you're just using the equivalence between like all convex combinations being
Yep.
real rooted,
Yep. Exactly,
and having a common interlace. Okay.
exactly.
Yeah. Okay. That makes sense.
Yeah.
Do we have any more questions before we resume?
A quick question. The original partitioning theorem it holds for real vectors. If we wanted a theorem about complex vectors, it seems like we couldn't go through this interlacing argument.
No, so it works for complex vectors. I just said real because I don't know, some people I guess wouldn't want to look at it, but all you need is that the matrices are Hermitian. So in the end, we're only interested in characteristic polynomials of Hermitian matrices, and they have real roots. So that's fine.
So you're only dealing with real polynomials in the end.
Yeah, the polynomials are always real, even if the vectors are complex. The polynomials are real.
Okay, thanks.
Good question, yeah.
And related to this, where is it that you use the fact that you have rank 1 vectors? I think you use it now with this equality. Do you also use it again?
Yeah, so let me emphasize that this identity is very strongly uses the fact that they're rank 1. Okay, so if they're rank 2, then this thing doesn't even have real roots. Basically, you can encode the quadratic polynomials type of examples in this. Okay, so I mean, the one thing that's really non-negotiable in this argument is a rank 1. And yes, so the rank 1 is what gives you this identity, and this is what we exploit in the brute bounding as well. So yeah, so without the rank 1, I mean, I mean, expected polynomials in general don't make sense unless you have rank 1.
Thanks.
Yep.
So before we resume, let me just mention, since we started a little bit late, the talk is being recorded. So if anyone has other constraints and needs to leave, please feel free to do so. Otherwise, maybe Nikhil, you can tell us what's coming up briefly, and then we move on to the shorter second part of the talk.
Okay. So what's coming up is the second part, which is how to bound the roots, assuming these facts about these vectors, right? So in the first part, I didn't assume anything about what these random vectors look like. And this is basically a quantitative analysis of what I did in the first part, right? So I showed you this identity in the first part that witnessed that the existence statement that there exists one point. Now I'm gonna analyze what this does quantitatively, and that will give me a bound. So should I start?
Yeah, I think so. If everyone's ready, there's no more questions. Yeah, please go ahead.
So okay, so in the first part I related some existence of some polynomial to the expected polynomial. Now I have to bound the roots of the expected polynomial, which is this is an analysis type of problem, right? I need some kind of effective bound on these roots. Okay, so how am I going to bound the roots of this expected polynomial? Well, I'm going to use this representation again. So I mean, there's a reason I called this a central identity. This is the structure in this problem that we exploit for everything. Now, previously I showed you that these operators, preserve real stability. So I know all of these roots lie on the real line. Now I need to know where on the real line. Okay. So the problem that I need to solve is given a polynomial that looks like this. It's a determinant of xi plus some zi ai, where ai are positive semi-definite with these operators. Where do its roots lie? I know they're on the real line, but where? And the way I'm going to achieve this is by understanding what these differential operators do to the roots of a multivariate polynomial. Okay. So the determinant of a sum of PSD matrices, its roots are actually very easy to understand. Okay? It has no roots where all the coefficients are positive, for example. What I'm going to do is start with that understanding and then figure out what these operators, how these operators change the roots, okay? And then track these changes until I get the polynomial I'm interested in. And you want to view this as a quantitative version of the fact that these operators preserve real stability. In the first part, I just used that they preserve real stability. Now I want to know where do they move the roots of these multivariate polynomials. Okay. So to warm up, let me do the univariate case. Okay. So in the univariate case, real stable polynomials are real rooted. And the basic question is, if I have a real rooted polynomial and I apply this 1 minus differential operator, what does it do to the roots? Okay. So it gives me a new polynomial. What do the roots of that polynomial look like? So the answer to this is interlacing again. Okay. Namely, if I have a polynomial p with real roots and I look at p minus p prime, the roots of that interlace the roots of the original polynomial. So let me show you a very short proof of this fact using rational functions, which I'll then generalize to do the multivariate setting, and which will give me quantitative bounds. So suppose I have a polynomial p with n roots lambda 1 through lambda n, and let's assume they're distinct for now. So I'm interested in p minus p prime, right? I minus this differential times p. P prime has, looks like this. It's a sum of all n minus 1 y's products. So I'm interested in the roots of p minus p prime. And I'm going to study them by looking at an associated rational function, p prime divided by p. Okay? So p prime divided by p is equal to the sum of 1 over x minus lambda I, where lambda I are the roots of p. It's a rational function with n poles. Okay? So let's see what this looks like. So here's p. It has 3 roots, let's say, on the real line. And I'm going to be interested in this rational function p prime divided by p. So it looks like this, okay? It has poles at all of the roots. And after the last root, it is positive and goes to 0 as x goes to infinity. Okay? Now, I can read the roots of p prime off from this rational function. Okay, so if I look at the places where p prime over p is equal to 0, those are the roots of p prime. That's because the roots of p have multiplicity 1, so p prime and p don't share any roots. So the intersection points of these curves with the real line are the roots of p prime. Okay, great. Now, this actually already proves to me that p prime interlaces p, by the way, right? So it's clear that in each of these intervals, as this rational function goes from plus infinity to minus infinity, it intersects the real line exactly once. So I just proved to you that p prime interlaces p. But I can actually read off much more from this function. Okay, so let me look at the level set where the rational function is equal to 1. So let me look at the set of all x where p prime over p is equal to 1, right? So that intersects. So that's a set of 3 points. So each of these curves. So there are 3 intersections with these curves. And now the point is that these are actually just the roots of p minus p prime, because if p prime is equal to p, then p minus p prime is 0. So I can read off the roots of p minus p prime, or p minus any constant times p prime actually, by just looking at the level sets of this rational function. Okay, so the level set of value 1 gives me the roots of p minus p prime, and again, this picture shows me that p minus p prime interlaces p. Between every 2 roots of p, the roots of p minus p prime alternate with the roots of p, and are, for example, greater than or equal to them. Okay. Okay. So what I'm going to now try to do. Yes.
Why do you know that all the roots are distinct? I mean,
I'm assuming they're distinct.
You're assuming they're distinct.
Yeah.
Okay.
Okay. Okay. So now so the basic concept is looking at the level sets of this rational function tells me about the roots of p minus p prime. So I'm going to try to make this, I'm going to try to go with this. So I'm going to call this the barrier function, p prime over p, but it also has many other names. It can call the Stieltjes transform or the logarithmic derivative. I mean, it's a very natural rational function. And I'm going to observe that this rational function gives me a way to find an upper bound on the roots of p minus p prime given the roots of p. Okay. So suppose I have p, and I can find a number b that's bigger than all the roots of p. Okay, that's above the spectrum of p, such that the barrier function at b, this rational function at b, is strictly less than 1. Right. Suppose I can find such a point. Then this point is an upper bound on the roots of p minus p prime. Okay. The reason is simple. The reason is that above the roots of p, this barrier function, this rational function, is strictly decreasing, right? So if I find one point where it's strictly less than 1, then it will remain less than 1 forever. And in particular, this level set, where the barrier function is strictly less than 1, contains no roots of p minus p prime. Okay. So I'm turning this algebraic problem of locating roots of p minus p prime into this analytic problem of studying level sets of this rational function, the barrier of p. Okay. But what if I want to do it again? What if I want to apply this I minus differential operator again, right? To do that, I would need some control of the level set of the barrier function of I minus differential, I minus d times p, right? P minus p prime. And currently, I don't have a way to do that, right? Currently, if I can control the level set of the barrier function of p, I get just an upper bound on the roots of p minus p prime. I don't get information about the level sets of the barrier function of p minus p prime. Okay. So it turns out that if you look at different level sets, not just the level set strictly less than 1, but a more robust level set. So let's say, given a polynomial, you look at the set of points for which phi of p is strictly at most half. Okay. Then it turns out a stronger theorem can be proved, and we've essentially proved this in this paper with Batson and Spielman. And what the theorem says is that if you look at the half level set of p minus p prime, it's basically the half level set of p plus 2. Okay. So, I mean, basically what this does is it relates the level sets of the barrier function of a polynomial p to the level sets of the barrier function of I minus d times p. Okay? And you can view this as a robust version of the argument I showed you earlier. And pictorially, the way you use this argument is the following. It's very simple. You just use it inductively. So you start with a polynomial p. You look at this level set where the barrier function is at most half. Okay. So this contains no roots of p and no roots of p minus p prime by the argument I told you earlier. But the lemma tells me that when I apply this perturbation, when I apply this operator I minus d, this level set just moves by 2. Okay. So my upper bound on the spectrum, my region of no roots, moves by 2. And now I can just keep doing it, right? I apply another I minus differential operator. Again, this level set moves by 2. And so this argument I can iterate, okay? I can analyze, this type of argument gives me control over the level sets of the barrier function of I minus differential to the k of p for any k, right? Any number of operators. And since these sets do not contain any roots, it gives me upper bounds on the roots. Okay? Are there any questions about this argument? Okay. So what I'm going to do now is generalize this to the multivariate setting, right? I'm going to track the roots by studying level sets of the associated rational functions. So here's what I want to do, right? I'm given a polynomial p. It's real stable. It has some roots in the plane, let's say, and I want to bound the roots of I minus partial x, I minus partial y of p. Two different differential operators, right? So here's an example of a real stable polynomial, and this is what its root surfaces look like in the plane. I'm interested in I'm interested in applying a perturbation I minus partial y, right? So I can just plot this on a computer, and it turns out it looks like this. If I look at I minus partial y of p, it looks like the root surfaces just move up, basically. Okay? They more or less, I mean, okay, that's not a formal statement, but they sort of move up. Now, the question is, can I prove this? Can I somehow formally prove that these roots move up? Okay, in the end, I'm interested in the locations of the zeros of this polynomial. Can I say something predictable about them? So I'm going to try to use the same approach. I'm going to look at related rational functions. So I'm going to define a bivariate barrier function, which has two coordinates, and the first coordinate is partial with respect to x of p divided by p, and the second one is partial with respect to y. This function is just the gradient of log p. Okay. And now, instead of again, to study the location of the roots, I'm going to look at a certain level set of this bivariate barrier function. Okay, so that's this red set here, and again, the set is going to not contain any roots of p. Now, what I'd like to prove is that when I apply this I minus partial y operator, this level set moves up by 2. Okay, just moves up, doesn't move to the right. Okay, so I want to be able to say that this region of non-roots moves in this predictable manner. Now, how am I going to reason about this, right? So in the univariate case, the rational function was very simple. You could draw it easily, and all of its properties were sort of very clear, like the monotonicity property that I used. In the bivariate case, the picture is not really so clear. I have this bivariate rational function, right? So here, there's this sort of amazing representation theorem, which is a major ingredient in the proof, due to Helton and Minikov, which says that all bivariate real stable polynomials are determinants of positive semi-definite matrices. Okay, so any p of xy is a determinant of xa plus yb plus c, where a and b are positive semi-definite. Okay, so this is sort of an amazing theorem because it tells you that locally, for all bivariate restrictions, all real stable polynomials look like determinants. Okay, so the whole power of this proof came from the point that we started with a determinant and applied some of these differential operators to get polynomials that encode the structures we're interested in, but are no longer determinants. Okay, this theorem tells you that actually all their bivariate restrictions are still determinants. So you left the space of linear algebra by looking at expected polynomials, but then by this theorem, you still have this determinantal structure. So basically, once you have this theorem, it sort of immediately tells you that these bivariate barrier functions behave essentially the same way as the univariate ones. And essentially the same proof, which is like less than a page, works, and you can prove the following theorem. So when you apply a differential operator with respect to x, this level set of the barrier function moves to the right. When you apply it with respect to y, it moves up. But basically, these different operators, which correspond to different random vectors in my original problem, behave independently. Okay, in this high-dimensional setting, they move this in independent directions, which is why there's no dependence on the number of vectors or on the dimension. Anyway, the end result is the following theorem: that if you have a polynomial like this, and the matrices have bounded trace and add up to the identity, then the roots are bounded by 1 plus epsilon squared. Okay, and since the matrices are just the covariance matrices of our vectors, this yields this theorem that we wanted. Okay. And again, the basic principle is just that, if you want to track roots of multivariate polynomials, you should do it in a multivariate way by studying what these operators do. By studying what these operators do to some canonical rational functions. Okay, so that's the end of the proof. So I bounded the root, and in both cases I used exactly the same structure, namely that these expected polynomials have this representation. Okay.
Nikhil?
Yep.
Yeah. Could you say a word as to why the bivariate case is enough? I mean, because you have more.
Yeah. So the bivariate case is enough because in this picture, right? So the statement that you want to prove is that when you apply I minus partial x, you want to say that the level set moves to the right and does not move up. Okay. that is a bivariate statement. You only need to consider two directions to prove that statement. You need to prove that it moves in one direction and not in another direction. Okay. So in the multivariate setting, basically, intuitively the statement you prove is that when you apply differentiation in some direction, that doesn't affect some other, every other direction, and that's a pairwise sort of condition. Is that clear?
Maybe you can also.
Yes.
Excuse me?
Sorry, I meant yes, that's clear.
I mean, you use the fact that these level sets are product sets. That's important, but yeah. Okay.
Nikhil, maybe you can just point us to where you use the fact that all vectors are short. Like, what happens if just one of them is the flat one, or it should break, right?
Yeah. So here you use. Okay. So this epsilon. So again, in this picture, right? These directions correspond to vectors, right? And in this proof, what's happening is that these things are sort of acting independently. Okay. So in this final bound, what you get instead of 1 plus epsilon squared is you get the maximum trace. Okay. So.
I see. Okay.
I mean, yeah. So basically, the bound on the roots that you get is determined by the maximum, not the some aggregate. Okay. Yeah. So okay. So that that finishes the proof of the root bounding, which finishes the proof of the theorem, which finishes the proof of this partitioning thing that I told you about, right? That if you have two vectors, you can partition them into sets, which preserve the spectral properties of the original set. That finishes the proof of the theorem. So let me just end with some open questions. So this proof was based on quantitatively analyzing what certain stability-preserving operators do to the roots of a multivariate polynomial, and we got a lot of mileage out of that. And I think there should be more such quantitative analysis of other stability-preserving operators, which can encode other structures. So far it's all been about preserving real stability, but by actually tracking the locations, we got these effective results. There should be more applications of this. So again, because you can encode a lot of things as quadratic forms. This is not algorithmic because in order to actually find the point in the probability space, you need to compute these polynomials, which are in general sharply hard to compute. So is there a way to do some approximation in polynomial time? And I think the most interesting question is why is this happening, right? So, I mean, we use this structure, this expected characteristic polynomial, to tell us that some good object exists, which is quite rare, right? But why does the existence of this object show up in this global structure, the expected characteristic polynomial, right? And why does it give such sharp bounds? So if you use this, I mean, you can use this to construct Ramanujan graphs, right? And it gives exactly the right bound. So there should be some general theory as to why these expected characteristic polynomials, encode all of the structure. And I'll just point out that already the constant term of these polynomials has been around for a long time. So if I give you diagonal matrices, the constant term of the expected polynomial is called the permanent. And if I give you Hermitian matrices, it's a mixed discriminant, which has to do with mixed volumes. So somehow this polynomial is encoding, a lot of interesting structure, and it should be part of some broader theory as to why. So that's it.
Okay, thank you very much.
Thanks.
Are there any questions?
Yeah, could you say, so what exactly do you have to compute to make this algorithmic? I mean, I guess naively.
Yeah, so what you have to compute is, it comes down to this thing, the same question here, right? So suppose I want to set the first bit, right? then I need to compute the expected characteristic polynomial conditioned on the first bit. That's what I need to compute. So you need to compute conditional expectations of characteristic polynomials.
Okay.
And as
So
I said,
you need the full polynomial. You can't evaluate it at a few points or something like that.
well, you don't need the full polynomial. You just need to know what the largest root is. So if you have a way of doing that without computing the polynomial, then great.
Right. Got it.
So yeah. I mean, computing the coefficients is somehow different. I mean, so all the hardness results are for computing the coefficients exactly.
Right.
Yeah.
Makes sense.
So you're saying in particular something something naive, like just Daniel, can you please mute your microphone? It's terrible feedback there. So Nikhil, you're saying in particular something naive is just randomly sampling and taking the average. That's not going to give you any good estimate of the largest root.
I don't think so, right? Because I mean, well, not in general. So I mean, even by yeah, not in general. You need to use some special structure of your polynomials to say that this averaging argument is actually, sort of robust. That there isn't just one, there are many or something like that. Yeah, so it's easy to construct examples where not in general. But so, for example, one case where I suspect this, where I think a good place to start looking for an algorithm is in this application to constructing Ramanujan graphs, where you use this to find good lifts of graphs. And there, the expected polynomial is the matching polynomial of an expander graph, which is a sort of known object, and is there's some feeling that it should be robust when it's an expander, because actually the object you're looking for is not even that rare. It occurs with probability like 52% or something. So maybe in that case you could try what you're saying, just randomly sample a few or something.
Okay, thanks.
Sorry, Nikhil?
Yeah.
What did you say? Where did you say the permanent popped up? You said the constant term is the permanent of sum of vi transpose?
Yeah, so what I said was that, so here's the expected characteristic polynomial of sum of vi transpose, right? If I, yeah, okay, so really I'm making a statement about, so this polynomial is equal to, it's a function of the covariance matrices of the vi, right? And in the case where all the covariance matrices are diagonal, the constant term of this polynomial is the permanent of the matrix that you get when you take all those diagonals as columns. Does that make sense? So this is an n-variate polynomial. Its constant term is, well, it's just the expected determinant of these things. And yeah, when you plug in diagonal vectors, you get the permanent. I mean, you seem unsatisfied by this. I mean, I'm just saying that if you.
Sorry, we're muted. We're muted. Yeah. Okay. Thank you.
Muted. Okay. If you just take this and plug in diagonal matrices, you get the permanent as a constant term.
Oh, okay, I see.
But in your case, they're rank 1, right? So you can't really get anything interesting this way.
No. So, well, what I mean is if the covariance matrices.
Oh, right. The whole sum, right.
Yeah.
Okay.
If they commute.
So you take that diagonal matrix, and then you take the diagonal entries and form a column of another matrix.
Exactly.
And then, yeah, that matrix permanent. The permanent of that matrix is the constant term.
Exactly. I mean, one concrete way to view it is if you construct if you look at the distribution of random lifts of a graph, then these polynomials are just matching polynomials. So the constant term is the number of matchings, which is the permanent.
Yeah. All right, thanks. How important is it that the VIs have finite support?
It's not important at all. We just didn't want to deal with. Yeah, so.
Right.
Do you believe the statement is still true when when you're dealing with the higher rank, the non-rank 1 case? What's your conjecture?
So I don't think it's so. It's, I mean, yeah. I don't know. I don't have a conjecture. I'm not inclined to think it's true in the non-rank 1 case, actually. But why is that? Yeah, I don't really have a counterexample. I'll think about it. I'm inclined to think it's false, but yeah. So. I mean, so one natural direction to explore is to see whether this has anything to do with the like discrepancy theorems, like Spencer's theorem, and I mean, it seems different. I can't see the rank 1 structure there, but obviously that is true, right? So there's some, but that's sort of the diagonal case. So maybe, I mean, it's not clear if the thing that's stopping you is the non-commutativity plus the high rank or something like that. But yeah.
Yeah.
Do we have more questions? There's been a lot. If there's no more questions, what I can do is end the live broadcast and release this. Anyone who wants to go and anyone who wants to stay and ask more questions is welcome to stay. The window is not going to close. I'll just end the live. Let's thank Nikhil again for his talk. And thanks everyone for staying.